Okay, here we go. Chemistry 3101. So we're going to get started here with Chapter 1, a review of general chemistry, electrons, bonds, and molecular properties. Um, like I told you before I started recording this, if you have a question, just unmute your mic and ask me, or type it in the chat. I'll keep my eye on that. But let's get started with a review of general chemistry. You got to have a pretty good knowledge of general chemistry to tackle organic chemistry. So as I was saying before, what are some of the concepts that are going to be covered in this chapter? I would say a big one is going to be Lewis structures. So Lewis structures will be huge. Another thing would be molecular geometry. Molecular geometry. Another big one is hybridization. So hybridization. If you don't remember that word, it's when you have something, let's say a carbon that's sp3 hybridized or sp2 or sp hybridized. What else? I'd say another big thing would be intermolecular forces. So I'll just abbreviate those as IMFs, intermolecular forces. So if you remember London forces, dipole-dipole forces, and hydrogen bonding, those will be important concepts as well. But let's start out with a little bit of the history of organic chemistry and what the study of organic chemistry is. So section 1.1 is a very short section, but organic chemistry, what it is, it's nothing more than the study of carbon-containing molecules and their reactions. So we're going to focus on one element. If you took general chemistry 1 and 2 at UCCS, that would be chemistry 1401 and 1411. And if you think about those classes, you focused on pretty much the entire periodic table. You talked about a lot of the periodic trends, electron affinity, ionization energy, all of those things. And now you're going to spend 2 semesters focusing on one element of the entire periodic table. And why is that? Well, there's some very good reasons for that, which are going to become abundantly clear as we move through the content. But more than just studying carbon-containing molecules, we're going to talk about what happens to a molecule during a reaction. And if you remember from general chemistry 2, you would have talked about reaction order a lot when a reaction is first order and second order. And so we know that molecules have to collide in order for there to be a reaction. We know that bonds are broken and bonds are formed. Again, going back to the beginning of general chemistry 1, you would have talked about chemical processes and physical changes as well. And what's the distinguishing feature, between a physical process like evaporation versus an actual reaction, a chemical reaction, is that bonds are broken and bonds are formed in an actual reaction. And so you can see here, this is a reaction of a hydroxide ion. So you should know that ion. You should have seen that Avogadro's number of times in general chemistry 2. But you see the hydroxide here is reacting with this compound. This is called iodomethane. Iodomethane. And the name is not important for the first quiz. Okay, this is just a review of general chemistry. But you see the reaction between the two. And this first arrow here represents a bond being formed. So this is a bond being formed. And then the second arrow represents a bond being broken. Okay, and we end up with a new compound. This is methanol or methyl alcohol. And then we have an iodide ion out there as well. But if you notice, what are we really looking at here? As I talked about this reaction, I wasn't really talking about the carbon atom a whole lot. I was actually talking about the electrons, because you can see that the bond that is being formed from this pair of electrons on the hydroxide. And then you see that the pair of electrons in this bond is being broken to form the iodide ion. And so what are we really doing in organic chemistry? What we're actually doing is we're focusing on electrons. So believe it or not, you're going to take 2 semesters in organic chemistry to answer this question: is why do reactions like this occur? But again, we do focus on carbon, obviously, in organic chemistry, but really if you break it down to what it is, it's talking about electrons most of the time. So how do we distinguish between organic and inorganic compounds? Well, there's some really interesting history with this, and you can read about it in the textbook. But it talks about how scientists and philosophers thought, okay, well, we have organic compounds, and then we have inorganic compounds. And the difference that they thought historically between the two is that organic compounds came from living organisms, and inorganic compounds came from things like minerals, things that were not living. And so they said that's the difference between the two. And they said, Well, the organic compounds must come from some kind of vital source, and they called this vitalism, where they said there has to be some higher power involved in making organic compounds, because they said, well, when we try to heat an organic compound, oftentimes they decompose. And so what happened is that Friedrich Wöhler did this experiment in 1828. So 1828, 1828, he did this experiment where he took ammonium cyanate, which does contain carbon, but is considered to be an inorganic compound. He heated that up and he made urea, which is an organic compound. You know that urea is found in urine. And what he stated was, when he did this reaction, is he published this and he said, I was able to make urea without the aid of dog or man. Okay, so he had isolated urea from dog urine before and from human urine, but now he made it from something completely inorganic. And so that blew the lid off of vitalism. And then, things moved relatively quickly from that moment forward. And that people said, well, organic compounds are actually compounds that contain carbon. And then they went on from there. But, where do we find organic compounds in our everyday life? Well, places that you would find organic compounds naturally would be things like cotton. If you think about the clothing, most of the clothing that you wear is made of cotton, which is a polymer of sugars, put together, which are organic compounds. What else? If you think about things like wool and silk, those would also be considered organic compounds. Also synthetic compounds like polyesters, nylon, Kevlar, polyethylene terephthalate, okay, plastics. Those are all organic compounds as well. So, something my wife and I will argue about sometimes is she'll say, these bananas are organic. And I said, well, garbage bags are organic too. So should I eat those? So I hope something is organic if I'm going to be eating it, boy. And then something that's near and dear to my heart is I worked in the pharmaceutical industry for a long time. And so I'm always fascinated by drugs and, always interested in medicines. And so if you're interested in medicines at all, good news is that our textbook talks about them quite a bit. And so if you're interested in any kind of drug, those are going to be organic compounds as well. Anyhow, I won't spend too much time talking about that, but let's get into section 1.2, structural theory. So first section's done, the course is practically over, right? Anyhow, so by the mid-1800s, it says here that it was first suggested that substances are defined by a specific arrangement of atoms. So specific arrangement. And so what you guys know at this point is, if I was to say, well, let's say I have a compound and its formula is C2H6O. And you guys have studied General Chemistry 1 and General Chemistry 2, and you say, well, I can't tell you what compound that is, Mr. Dion. I'm going to need more information than that. So the formula is not an adequate description of the compound. Why? Because you can actually have two isomers with this formula, C2H6O. We call these constitutional isomers. Why? Because they have the same constitution. They're both made up of 2 carbons, 6 hydrogens, and 1 oxygen. But are they the same compound? The answer is absolutely not. You see here we have dimethyl ether, which has a boiling point of negative 23 degrees Celsius. That means at a room temperature, it is a gas. Okay. And then we have ethanol, which is the alcohol found in alcoholic beverages, which has a boiling point of about 100 degrees higher. Okay. Could anybody answer this question? Why is it that ethanol would have a boiling point that is so much higher, so much higher than the boiling point of dimethyl ether? Could anybody answer that? Or give me an idea as to why that might be? You can either type your answer in the chat, or you could unmute your mic. So there's a specific reason why ethanol has such a high boiling point, whereas dimethyl ether doesn't. Okay. What if I said, yeah, there you go. Thanks, Aaron. It has to do with intermolecular forces, doesn't it? Right? It has to do with intermolecular forces. Okay. So what's the major intermolecular force, or the strongest of the intermolecular forces found in ethanol? I'll give you a hint by circling this part of the molecule right here. It's hydrogen bonding, right? You see that ethanol has hydrogen bonding, okay? Whereas dimethyl ether does not have hydrogen bonding, okay? It only has a dipole and a London force. And so we know the intermolecular forces, the hierarchy is hydrogen bonding is the strongest, and then we have dipole-dipole, which are in the middle, and then you have London forces, which are the weakest of all. So that's something that you will need to know for this chapter, and I'll get into it later on today. Anyhow, so atoms that are most commonly bound to carbon. Well, we saw in the previous slide that you could have an oxygen bound to carbon. Turns out you can also have nitrogen bound to carbon, the halogens, hydrogen, obviously. And so these are the atoms that we're going to talk about a lot in this chapter. And in this entire class, we're going to talk about carbon, nitrogen, oxygen, hydrogen, the halogens, fluorine, chlorine, bromine, and iodine. And you should know how many bonds each one of these atoms forms when it's neutral. So we say that carbon is tetravalent. Why? Because it forms 4 bonds. So that's where tetra comes from. You might remember the prefix tetra. Let's say you have, tetramethyl or something like that. Then we have trivalent. Well, trivalent is what nitrogen is. So nitrogen forms 3 bonds. It normally has 3 bonds and 1 lone pair. So I'll scribble in the lone pair here. And you would see that in something like ammonia, for example. I'm not going to draw the structure right now. Divalent. So what is divalent? Oxygen is divalent. Okay, it forms 2 bonds. It normally has 2 bonds and 2 lone pairs. Where would you see that? Well, if you draw the Lewis structure of water, okay, water, the oxygen in water has 2 bonds and 2 lone pairs. And then finally, monovalent. So hydrogen and the halogens, those are monovalent, meaning they only form 1 bond. So, students like to know rules that they can just say this never changes. Well, in organic chemistry, I'll just tell you right now, the hydrogen, fluorine, and all the rest of the halogens, they're only ever going to form 1 bond. Okay, I know that chlorine, bromine, and iodine in general chemistry, sometimes you'll see compounds where those can form more than 1 bond. But in this class, the halogens, so read my lips, okay? Halogen and the halogens, and hydrogen, they only ever form 1 bond in organic chemistry. They do not form multiple bonds in this class. So let's review. Okay, carbon forms 4 bonds. Okay, a good example of that would be something like methane, which is the simplest possible organic molecule in the universe. Then we have ammonia. The nitrogen in ammonia is trivalent, forms 3 bonds, 1 lone pair. Oxygen is divalent, 2 bonds, 2 lone pairs. Okay, let me ask you guys another question. Let's say I was to draw the Lewis structure of water. Okay, just kind of testing the waters here, no pun intended. Okay, there's no trick questions in my class, none. If there's one thing I detest, is trick questions. Okay, if you look at this bond here, if I just draw a little line or a little arrow to that bond, when you have a bond between 2 atoms, this is not a trick question. How many electrons are in that bond? Anybody? How many electrons are shared between 2 atoms when you form a covalent bond? Exactly. There's 2 electrons. There's 2 electrons in any bond, okay? It doesn't matter if it's a sigma bond or a pi bond, there are always 2 electrons. Okay, so with that in mind, it says draw all of the constitutional isomers with the following molecular formula. So we have C3H7Cl, and then we have C4H10. Well, let's start with the first one. Okay, so the first one, we have 3 carbons, 7 hydrogens, and 1 chlorine. Now, what did I just tell you about hydrogen and chlorine? How many bonds do they form 100% of the time? 100% of the time, 1, okay? So if you remember from General Chemistry 1 that chlorine always has 1 bond and 3 lone pairs, okay, because it's a halogen, it has 7 valence electrons. Well, we know that carbon always forms 4 bonds, 1, 2, 3, 4, and we have a second one with 1, 2, 3, 4, and we have a third one with 1, 2, 3, 4. Okay, so we need to put all of this together to make a structure. Well, what are we going to do? Well, let me start by moving this down here. I'll just put this down here, and then we'll put times 3. So what that means is our only option is to put all the carbons together in some kind of chain like this, 1, 2, 3, and then we know that each one of them is going to have a total of 4 bonds. Give me a thumbs up if you're with me so far. Okay, I got 3 carbons in a row, and each one is going to form 4 bonds. Okay, now you know that the chlorine can't be in the middle, right? That would be a huge no-no. Why? Because chlorine only ever forms 1 bond. So the only possibility, logically, is to put the three carbons in a chain like this. Now what are we going to do? Could anybody give me an idea as to how I'm going to move forward with this problem? Yeah, I could put a chlorine on the far right. Sure, that'll work. So let's do that. So let's put a chlorine on the far right. There we go. And so now we've used up the chlorine, but we've got 7 hydrogens and we have 7 spots here for the hydrogens. So let's put this something like that. What do you think? Not too bad? There you go. Okay, I'd say that's a perfectly reasonable structure. However, it's not the only possibility. So what I'm going to do is I'm going to move this over slightly, and I'll just use the magic of the iPad to paste another version or another copy of it over here. Let's move that like that. And so what I'm going to do is I'm going to erase the chlorine. And so could anybody give me an idea as to what else I could do to make another isomer? Tell me how I could modify the second structure that I've drawn. And don't be shy, we're learning the subject. Yeah, put the chlorine in the middle? Sure, absolutely. I like the way you think. So let's erase that hydrogen. We'll put the chlorine here, put the lone pairs in, and put the hydrogen here like that. I'd say that's perfect, okay? Nothing wrong with that at all. I love it. Now, sometimes I'll have students say, well, what you could also do is this, is you could, what if you put the chlorine on the far left? Okay, so let's say I took the chlorine and I put it on the far left like this. Okay, what I'm going to do is I'm going to change the color here. So you notice the structure in red. Okay, so let me just change. No, we'll leave those two here. Anybody see the problem with the structure in red? Does anybody see there is an issue with the structure in red? It is not a new constitutional isomer. Could anybody tell me why the one in red is not a new constitutional isomer? It's the same as which one? It's the same as the first one. Absolutely. Absolutely. Couldn't agree with you more. There you go. So the problem is that what Kelly is saying is that this structure and this structure, those two are identical. Okay. Remember that molecules are tumbling around in space. Okay. They have freedom of movement. And so there's no difference between those two molecules whatsoever, the two in the green circles. Okay. If I was to take the one in red and flip it around 180 degrees, so let's say I made an axis like this, okay, and if I rotated it 180 degrees, I'm going to end up with this right here. So there's no differentiation between the two. And in fact, these are the only two constitutional isomers, are the two that I have in blue. So the answer is these two are the constitutional isomers of this formula. Okay, I should move my box over. I'm kind of covering up my chlorine there a little bit. But let me just, there we go. Okay, something like that. Give me a thumbs up if you're with me on that there's only two constitutional isomers for this compound. Cool. Awesome. Now, something that you could do is if you're struggling with it, if you're saying, I don't see why it is, why these two are identical, what you could do is you could make a model. Okay, and that's what you heard me doing. I was starting to build a model, which I didn't finish. But during the break, I could make a model and show you that, why those two are completely identical to each other. So I'm just going to erase this one here in the interest of time. And let's try the next one, C4H10. So now we've got 4 carbons and we've got 10 hydrogens. But we know that hydrogen only ever forms one bond. So there's one possibility would be to put, I'll use the red pen, would be to put all 4 carbons in a row like this. And we know that each carbon has to have a total of 4 bonds. So I'll start putting in my bonds like this. And then what am I going to do? What do you notice about these lines? How many lines do I have with nothing at the end? The answer is 10 of them. And so I'm going to put a hydrogen at the end of each one of these lines like this. All right, I'll put one here and one here. It's kind of a funny hydrogen. Is there anything wrong with this Lewis structure that I've drawn? And again, it's not a trick question. I'm not trying to fool you or anything. Is there anything wrong with this Lewis structure? No, it's perfectly reasonable. There's nothing wrong with it at all. Okay, it's a perfectly reasonable Lewis structure. Now, I'll just give you a hint on this one, because since we're just getting started, it's the first day of class. There is one other constitutional isomer for this compound. Could anybody give me an idea of how I could make that constitutional isomer, what I'm doing wrong? Or not what I'm doing wrong, but how I could modify the structure? There is a way I can modify it to make one more constitutional isomer. How would I make another constitutional isomer for this compound? Does anybody have an idea?
You can split the chain of carbons.
Yeah, so I can create a branch, right? I can't make a double bond. There's no way to make a double bond here. Okay, can't make a double bond, but I can alter the chain, right? Instead of having all the 3 carbons or 4 carbons in a row, what I can do is I can have a branch, okay? So let me show you what that would look like. So if we have something that looks like this, if we put 3 carbons together like this, and then we put one as a branch, like that. Now, if I highlight this carbon in green, could anybody tell me how many bonds is this carbon in green missing? That I haven't put in. Exactly, it's missing 3. So I'm going to put 1, 2, 3. Okay, I'm going to do the same thing to this one. 1, 2, 3, and then 1, 2, 3. Could anybody tell me how many bonds is this carbon missing? The second one that I highlighted in green. Yeah, exactly. It's missing 1. Okay, so there we go. All right, so these are 2 different compounds. Okay, so besides drawing constitutional isomers and saying, well, they're connected in a different way. Okay, so remember, the definition is this: constitutional isomers have the same formula, but a different connectivity, meaning they're connected in a different way. So we could scribble that down here. So same formula, Mr. Dion, formula, but different connectivity. That is a word. Connectivity. Okay, it's a word we use in chemistry to say they're connected in a different way. Now, besides just examining it with your eyeball or making a model, something that you're going to learn later on, and we haven't covered it yet, so don't worry about it for the first quiz, but I'll just show you, you're all old enough to hear it, is that another way you can distinguish between constitutional isomers is to name them. And if they have different names, then they're different compounds. Now, the first compound, and again, you don't have to know this for the first quiz. What's going on? Come on, you. There we go. You don't have to know this for the first quiz, but this first compound here, this is called 1-chloropropane. And this compound here is called 2-chloropropane. Again, the naming isn't important for today, but you can see they have different names, so they are different compounds. And then the ones in the bottom, this one here is called butane. If you're wondering, is that like the butane in a butane lighter? The answer is absolutely. And this one here is called isobutane. And so they have different names, and therefore they are different compounds. So that's another thing that you're going to use later on. But for the first chapter, we'll just use inspection. So we're just going to use our eyeball and say, well, these are connected differently, so they are different compounds. All right, so let's talk a little bit about covalent bonding. Again, you would have talked about covalent bonding and ionic bonding at length in General Chemistry 1. And so I already reviewed this with you, is that when we have a covalent bond, okay, the simplest molecule that you can have is an H2 molecule. I covered this with you, is that the bond or the line drawn between any 2 atoms represents a pair or 2 electrons, right? You guys know the word pair means 2. So 2 electrons shared between 2 atoms. And again, the simplest possible molecule that you can draw or that we can have is an H2 molecule, a hydrogen molecule. And what's being shown here in this graph, I know you would have seen this in general chemistry, but if you didn't understand it before, I'll explain it to you now. So if you have 2 hydrogen atoms, you should know that hydrogen is the first element in the periodic table. It has 1 valence electron, right? Hydrogen is 1s1. So if I draw a Lewis structure of hydrogen, it's just a hydrogen with a dot next to it, okay? So if we have 2 hydrogen atoms that are separated by some kind of infinite distance, okay? They're separated, they're really far apart, they're not interacting with each other whatsoever. whatsoever. But then as you bring them closer together, oh boy, they start to get attracted to each other. Now, why would that be? Why would they start to be attracted to each other and achieve a lower energy scenario? Well, the reason why is because, now listen to my words very carefully. The attractive forces between the valence electron of one hydrogen atom and the neutron in the other hydrogen atom, those are going to be maximized, right? The attractive forces between this electron and the neutron in the other hydrogen atom are going to be maximized. And the repulsive forces between the two electrons and the two neutron, or sorry, the two proton. Did I say neutron? I meant proton. I'm sorry. Okay, let me say that again. The attractive forces between the electrons and the protons are going to be maximized, and the repulsive forces between the electrons and the electrons and the protons and the protons, those will be minimized. Okay, so again, what's going to happen is the hydrogen atoms are going to get closer and closer and closer and closer and closer until they achieve this special distance, or they achieve an internuclear distance of 0.74 angstroms. So there's exactly 0.74 angstroms between the two nuclei, and it releases 436 kilojoules for every mole of hydrogen molecules that are formed. Now, this is what? This is the most stable distance between the nuclei. Okay, and that is how we measure bond length. We say, well, the most stable distance that you could have between them is 0.74 angstroms, and so that is the bond length in the H2 molecule, and you can see that it achieves a more stable state. And so this is essentially what covalent bonding is. If you've ever wondered, why do atoms come together to make a covalent bond? It's because they achieve a more stable situation, right? They become more stable. And so this is how we determine things like bond strengths and bond lengths. Anyhow, now that we've covered that, let's review something that I just misspoke on. Okay, I was bringing up neutrons. Okay, I think I need another cup of coffee. But anyhow, you should remember that a proton has a +1 charge and that an electron has a -1 charge. Okay, everybody good with me on that? Protons are +1, electrons are -1. I'm going to assume yes. All right. So protons and neutrons reside inside the nucleus. So you remember that neutrons are neutral. We don't talk about neutrons a whole lot in organic chemistry, except for when we're talking about isotopes, maybe carbon-13 or deuterium or tritium or something like that. And then electrons, like I said, which is what we're going to focus on, those reside outside of the nucleus, of course. Now, valence electrons, what are valence electrons? Those are the outermost electrons. And when we talk about bonding, when we talk about bonds being broken and bonds being formed, when we talk about chemical reactions, what are the electrons we're interested in? We're interested in the valence electrons. Why? Because those are the ones that are involved in chemical reactions. Now, just to review, if I was to ask you to come up with the electron configuration of carbon, could anybody tell me what the electron configuration of carbon is? It's going to be 1s. Anybody? Could help me out with that? If you look at a periodic table, where would I start for carbon? How many total electrons does carbon have? Total electrons. If you look at a periodic table, how many total electrons does carbon have? Can anybody hear me? Hello? All right.
It
Okay.
has 14 electrons.
Nope, definitely not. Okay. So how many total electrons does carbon have? So which element is carbon? It's element number what? Which element is carbon? It's element number 6. There we go. Okay, so carbon is element number 6. So if we go into our periodic table, that means that carbon has a total of 6 electrons, right? If it's element number 6, it means it has 6 protons and 6 electrons. So we'll say here carbon has 6 protons and 6 electrons. So what's my electron configuration going to look like? It's going to be 1s2, 2s2, 2p2. All right, so what are the valence electrons? Those are the outermost electrons. So those would be these 4 electrons right here. These are the valence electrons. And so now, if we want to draw a Lewis structure of carbon, it's going to look like this. Carbon has 1, 2, 3, 4 valence electrons. All right. So there you go. So now that we've reviewed a little bit of electron configuration and how to draw the Lewis structure of an atom, what if you wanted to draw the Lewis structure of any other atom? Well, again, we're not going to worry about metals a whole lot in this chapter. We're going to talk about main group elements. So if you remember main group elements, so I can scribble this down here. Come on, pen. Where are we? Main group elements. That would be the S and P block. S and P blocks, not the D block. So we're not going to worry about the transition metals. We're not going to worry about lanthanides and actinides this semester. So what you're going to do is you're going to look at the group number, if it's the A number, and that tells you the number of valence electrons. So group 1A, everything has 1 valence electron. Group 2A, everything has 2 valence electrons. Group 3A, everything has 3 valence electrons. So for example, boron, its Lewis structure would have 1, 2, 3. Carbon is group 4A, it has 1, 2, 3, 4. Nitrogen has 5, so 1, 2, 3, 4, 5. Oxygen has 6, 1, 2, 3, 4, 5, 6. Fluorine, chlorine, bromine, and iodine, those all have, oops, let me just draw it like that, 7, like that. And then, of course, helium is an exception. It only has 2 valence electrons because it only has the 1s orbital available to it. But all the rest of the halogens, sorry, the noble gases, they all have 8 valence electrons, right? Like neon would look something like that. So again, you should be able to draw a Lewis structure for any of those elements on the previous slide. And so how do we draw Lewis structures? Well, let's go over the rules quickly. We draw the individual atoms using dots to represent the valence electrons. Then usually, not all the time, but a lot of the time, we put the least electronegative element in the center. You can see with the example here, it doesn't work that way because hydrogen can only form 1 bond. But let's say you have ammonia. You know that nitrogen, as we just saw in the previous slide, has 5 valence electrons. Hydrogen has 1, and there's 3 hydrogens. So 5 plus 3 gives you a total of 8 valence electrons. So if we have our nitrogen in the center and we draw a bond to each one of the hydrogens, in this structure, the way that I've drawn it on the page right now, could anybody tell me how many valence electrons have I used up so far in what I've drawn in blue? How many have I used up so far? Yeah, exactly. I've used up 6, but I need 8. So where do the last 2 go? They're going to go on the nitrogen to complete its octet. So now the nitrogen has a complete octet. The hydrogens have their duet because hydrogen can only form 1 bond. And there you go. There's a perfectly reasonable Lewis structure for ammonia, just like that. All right. So just to review, if you're wondering, how do you know the nitrogen has an octet? You look at it and you say nitrogen has 3 bonds. Okay, so 1, 2, 3, 4, 5, 6, and then a lone pair 7, 8. So it's surrounded by 8 electrons. So it has a complete octet. All right, there you go. So that's a little bit about Lewis structure. So here it says for Lewis structures, now there are several, kind of modes of attack you can take to Lewis structures, but it says here draw the individual atoms using dots, put them together so that they make complete octets. You can do it that way. That does work, but there are other ways too. For example, like this compound here, C2H4. How many total valence electrons do we have for this compound? Well, there's 2 carbons. Each carbon has 4 valence electrons, so we'll put 4 times 2, and then each hydrogen has 1, and then there's 4 of those. So that gives us 8 plus 4, so that gives us a total of 12 valence electrons. Now we know that hydrogen only has 1 bond ever. Hydrogen always forms 1 bond. And so what are we going to do? I would start by putting the 2 carbon atoms together like this, and then I would draw single bonds to the hydrogens like that. Okay. Now, the structure that I've drawn so far, how many valence electrons have I used up so far in what I've drawn? 10. Exactly. I've used up 10. Where are the last two going to go? Well, do the carbons have complete octets? The answer is no. If I just look at one of the carbons, you can see that this carbon here is surrounded by 1, 2, 3, 4, 5, 6 electrons. So that doesn't satisfy the octet rule. So I have 2 electrons left over. Let's say I put one here and one here. What's the problem with that? Does the carbon have a complete octet now? The answer is no. It's surrounded by 1, 2, 3, 4, 5, 6, 7 electrons. So that doesn't work either. So could anybody tell me what the answer to this one would be? How do I modify this structure? Exactly. Thank you, Brooklyn. I'm going to put a double bond between the 2 carbons. Okay. Now, if I put a double bond between the 2, now I have a good Lewis structure, don't I? I see that both of those carbons are surrounded by, let's just try this one here. It's surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. The carbon on the right is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. So everybody is surrounded by 8 electrons, or both carbons are at least. Each hydrogen has 1 bond, so that looks completely reasonable. So now what we're going to do is we're going to tally up the total number of valence electrons for this compound. I'm going to give you a second here. I'm going to stop talking for a couple of minutes. Could you guys take a second and tell me if you can calculate the total number of valence electrons in this compound? Total number of valence electrons. And if you think you have the answer, just holler it out, or you could type it in the chat. Either one is fine. All right, somebody has an answer. Okay. Somebody says, okay, we have some differing answers. Let's take a look. So carbon has a total of 4. Hydrogen has 1. There's 4 of those total, 1, 2, 3, 4. So I'll just put them all here, 1 times 4. And then the oxygen has 6. So that gives us 8 plus 6. So that gives us 14 valence electrons. All right, 14 valence electrons. Now you notice that the way they've written this structure is kind of interesting, isn't it? They wrote CH3OH. Okay, they could have written this. They could have said CH4O. That would actually be the molecular formula of the compound. Does anybody know why they wrote it like this? CH3OH. And it's not a trick question. Does anybody know why they wrote it in that order? Why they put the hydrogen, one of the hydrogens out on the end? Exactly. Exactly. What they're trying to do is they're trying to give you a hint as to how the atoms are connected, right? You have a CH3 on the left-hand side, and then the OH is on the right-hand side. Exactly. So what we're going to do now is we're going to take a short break, and I would like everybody to try to draw a Lewis structure for this compound. Okay, it's all your homework is for the first break. So I'm going to stop recording here. Just give me a second.